So in this class we are going to talk about the design of digital current mode control using frequency domain approach. So here we will recapitulate the frequency domain design of analog current mode control, then we will discuss frequency domain design of digital current mode control in a buck converter, and then frequency domain design of digital current mode control in a boost converter. So here we are talking about a buck converter current mode control, and this diagram we have explained multiple times, and this is the analog control, and then it is a peak current mode control. Now when you are going for loop shaping of analog peak current mode control, we know that control to output transfer function, if we use a very simple approximate model, it can be written in terms of a first order model, and then we can find out the ESR 0 and poles and all, and this thing we have discussed in our lecture 38 in NPTEL, our previous NPTEL course. And the loop transfer function will look like this, where we need to select the suitable controller. Now we have discussed, if we take an ideal buck converter, or if the ESR is very low, then the ESR frequency due to the ESR, that means ESR 0, that frequency, it will be much outside the control bandwidth, as well as it can be even higher than the Nyquist frequency, half of the switching frequency. So it has almost no role in the closed loop performance because it is at much higher frequency. So in that case, we may not need to compensate for this 0, so we will assume we will neglect this effect. In that case, it can be written in terms of an ideal buck converter, that means as if this 0 is not there, and then it will be simply R by 1 plus S divided by omega p. Now we want to design a PI controller. So if you take a PI controller, it takes this form where omega Cz, that is the controller 0, will be Ki by Kp, and we are now trying to shape the loop. And if we shape the loop, how does it look like? By means of stable pole 0 cancellation, the loop will be something like a loop S by means of stable pole 0 cancellation R Ki by S. That will be our loop transfer function, where omega Cz is placed in coincidence with our planned pole, that is nothing but, then we can find out, that means this expression is this one, and we know that omega p from here, and since we are ignoring the effect of ESR, so we can simply write this expression. That means the proportional gain can be obtained, which is a function of integral gain and then load resistance and the capacitor. Now when you go to digital current mode control, we know that again we have discussed in lecture 40 that we may have to introduce that simple delay. That means the delay due to, what is the delay? That is due to the ADC or A to D conversion delay plus delay dPWM, and we know that dPWM delay is nothing but D into T. Now if we write the loop transfer function, compared to the previous one, only the delay term will come, and we have discussed this delay will not affect in the frequency response, it will not affect the phase gain plot, but it will affect the phase plot, because if you take the original analog loop transfer function, it is simply some gain by S. So the phase margin is 90 degree, and because of this term we will get an additional minus omega tau d. So that means the phase margin will be, in this case, what will be the phase margin? It will be 180 degree plus theta omega, sorry, it will be theta dot omega, which is nothing but 90 degree minus omega tau d. So by suitably selecting the gain crossover frequency, so this will be computed at omega equal to omega c. So this will be omega c, because we have to calculate the phase margin at the gain crossover frequency. Now what is the design step? So we have to first select the gain crossover frequency. So typically for current mode control, for voltage mode in a buck converter, we generally go 1/10 of the switching frequency, but in case of current mode we can slightly increase, and that we have discussed in our earlier NPTEL course. We can go effectively by 1/8 of the switching frequency, and if you select 1/8 of the switching frequency, and we know the phase margin computation, because if exact cancellation for analog, it will be 90 degree phase margin and it will be delayed version. So, there will be a phase lag. Now, depending upon the delay amount for the given delay, because you may have up to 1 cycle delay, if it is a switching cycle, full cycle delay, then omega c, what will be omega c? We have taken here 2 pi by 8 into Fs, which is nothing but 1 by t, and we are talking about tau d, which is also t. That means, what is my omega c tau d? It will be simply 2 pi by 8. It is in radian, and if you want to convert into degree, in degree, how much? So, it will be 2 pi by 8 into 180 degree by pi. So, if you cancel this will be 4. So, it will be around 45 degree. So, that means you will lose around 45 degree phase margin due to this delay. But that means for a given tau d, we may have to achieve in, because in current mode control very easily we can get, we typically want to achieve 60 degree phase margin in the conservative case. So, that means this will define what is the acceptable delay. So, if you have delay higher than that, then you need to sacrifice the phase margin. So, now if we want to achieve 60 degree phase margin for the given tau d, it may so happen that your 60 degree phase margin may not be met. Then you may have to reduce this, but in this current mode control, that omega c has no effect. It has effect, that means if we reduce the omega c, then we can reduce the phase contribution, because the delay we cannot do. Delay is coming from the digital controller based on what ADC you are using, what DPWM delay, we cannot do anything, but we can reduce this product term by reducing omega c. That means we have to reduce the crossover frequency. That means what our initial target was to achieve 1/8 of the switching frequency. In order to achieve 60 degree phase margin, you may have to operate below 1/10 of the switching frequency. This is due to you want to meet the required phase margin. Once if this is not satisfied, then you have to go to step 1, reduce the omega c, and then again cross check unless you reach 60 degree phase margin. Once it is met, that means you know what is my crossover frequency, then you simply obtain the integral gain by this omega c by r. Now, once you have, then we have to convert. Now, you see the integral gain is a function of load. So, if you want to get the worst case integral gain, maybe you should select a conservative choice. So, you should take the highest load current condition. Okay? Now, that means highest load current, which is that means if you want to get Ki to be, because the problem will be if you take a very large Ki, it may cause problem during the light load when R will be very high. So, we should choose a Ki which is the minimum value, and that is dependent on omega c into R max. Then what is the maximum load resistance? So, this will give the Ki minimum. Then we want to convert analog PI into digital, and it is a straightforward way. This is an analog PI controller. We already know Kp is a function of Ki into Rc, and we already have found Ki to be omega c by R, and we have already selected omega c based on the required phase margin criteria. Now, we want to convert the proportional all this analog controller gain into discrete time, and proportional gain will remain same. Integral gain will be simply the analog integral gain minus the into the sampling time, where the sampling time is same as the switching period. So, by that way we can design the controller by using backward difference formula. Now, when we go for a boost converter, then in a boost converter, if you write the loop transfer function, then DVC, which is a control to output transfer function, will have a right of plane 0 in a boost converter, and that is also discussed in our lecture number. I think it was discussed in lecture 39 in our NPTEL earlier course, earlier course. So, then if we have this RHP0 and these expressions are already given. So, this is the expression omega RHP0, that is the right of plane 0, then this is the pole. Now, we want to design a type 2 compensator. Why? Because in case of type 2, actually there should be another S. Type 2 compensator, the controller in case of PI controller, we will have a just 0 and 1 pole at origin, but in type 2 we have an additional pole, and that is needed to anticipate the effect due to the RHP0, because the controller pole, where this is the controller pole, sorry, this is the planned, the loop transfer function. So, I think this is all right, because this part is our GVC, So, we have to design the controller. So, the controller is this form. Then what is the loop transfer function? So, loop transfer function now after this compensation will be sum gain divided by S into 1 minus S omega RHP divided by 1 plus S omega RHP. Okay, so, a loop transfer function, and now we want to design. So, the summary is that this is the loop transfer function that we have discussed. This is a controller, and this is the loop transfer function we are writing in terms of KL, and here we are using this term because it is common. Now, we can do a normalization by selecting omega n to be omega by omega RHP. Then we already know that gain plot can be written as KL by omega n, because this term and this term, their gains are identical. So, there will be 1, and the gain will be primarily because of this term and this KL, but the phase will be this term, and then what we will get, the phase margin will be 90 degree minus tan inverse of this, and this will be computed at the crossover frequency, and this is discussed in lecture 36 in our earlier NPTEL course. Now, we want to design a digital current mode control. In case of digital current mode control, we have this additional delay, and it will affect the loop transfer function in terms of phase. It will not affect the gain will remain the same, but the phase will be affected. There will be an additional phase lag of minus omega tau d. That means, if you want to design based on the crossover frequency, we can first set in current mode control analog, we typically can achieve the crossover frequency 1/3 of the RHP0. So, we will start with that point, then we will compute the phase margin, because we have an additional phase lag due to the delay. So, given delay, if the delay is given, then we need to check, can we meet a phase margin of 45 degree or not. If it is not, then you need to reduce the crossover frequency. If not, go to step 1, reduce K. So, that means the factor is reduced, so crossover frequency is reduced, and you iterate this process till the phase criteria is met. Once it is met, that means for a setting the suitable value of omega c, then you can compute the Kc from this expression. And after computing this, that means you got the controller gain, and now all the controller parameters are known. So, now we are summarizing the equation. This is my controller, and the first controller 0 is to planned pole, which is 1 by 2 RC. Then the controller pole is nothing but the RHP0, in coincidence we are placing, this is also known. Then this we have just computed right now. This is computed in such a way we can achieve the desired phase margin, which is typically 45 degree. Then once we get, that means in this control all the values we know. So, the controller parameters are known, but it is in analog domain. So, you have to convert this analog into digital by means of backward difference formula, where we need to place S equal to 1 minus Z inverse by T, where T is the sampling time, which is same as the switching period, because we are taking uniform sampling at the rate of the switching frequency. And then we can convert this GCZ in this, and then if you append the inverse Laplace, we can write the expression of difference equation of the controller, and that we can also discuss. So, we are going to take the case study of digital current mode control for both buck and boost in the subsequent lecture, when MATLAB case study, when we want to design by this frequency domain approach in using continuous time model with delay, and we also want to discuss with direct digital design, that means in time domain, and we also want to show some case study with the direct design and this frequency domain design, and there we want to show the MATLAB simulation case study. So, in summary, we have discussed, we have recapitulated the frequency domain design approach of analog current mode control. We have discussed the frequency domain design of digital current mode control in a buck converter. and we have also discussed frequency domain design of digital current mode control in a boost converter, and we will be taking MATLAB simulation case study in the subsequent lecture when we also consider the direct digital design, as well as we also want to consider the large signal based current mode control design. That is it for today. Thank you very much.